first, I'd like to thank the organizer for this really nice conference. So, my name is Fabian. I'm from the University of Tokyo. So, for me, it's close to come to Tokyo, but I always like to come to Tokyo. And the work I present here is joint work with Patrick Hose at the University of Singapore. And what I'm going to talk about is kind of measurement disturbance relation using entropic methods. So, I mean, I guess uncertainty relations are really fundamental in quantum physics. So now I have to confess that I'm more from the physics side, from quantum information theory. So my perspective will more be from quantum information theory. So in quantum physics, a really fundamental kind of limitation is that certain observers are actually complementary, so they commute. In the following, I will always talk about X and C, and this X and C will be complementary observers. Of course, if they commute, then this is kind of, I mean, it's not interesting for us at this point. And the POBM measure, I will just with indices. So actually, my approach to uncertainty is more that I think that any kind of limitations to this complementarity, which actually comes only from this complementarity, and any limitation is, I would call, an uncertainty relation. So it all started with Heisenberg and this seminal paper in 1927. There he actually had the intention, or the idea that with this new kind of matrix mechanics, wave mechanics, actually to find an intuition about physics, because the classical intuition didn't apply anymore. So he was asking, can we actually revise our intuition and get a more fundamental understanding and intuition actually about quantum physics? And this led him to this uncertainty principle. So in uncertainty principle, we have kind of two different things. I mean, it kind of turned out in the future that there are actually two aspects of uncertainty, or at least two aspects. And one of them is preparation uncertainty. And I think this is the one which most of you know about, and most, I mean, is pretty well understood. Another part is measurement uncertainty. So in measurement uncertainty, I'm asked, or the negative formulation would be like, that there exists, I mean, if I have non-commuting observables, and there exists no joint observable which actually implements both measurements with perfect accuracy. And there's another kind of like formulation, I mean, there are kind of like different formulation, which just means that if I attempt to measure, to measure X, then I generally disturb C. So let me quickly just go to preparation theory. Preparation theory, as I said, I mean, what's the question there is that I have some preparation, and the formulation is that actually there is no preparation in which X and C are both kind of predetermined. And this has been made precise by Kennard and Robertson at the beginning by using variances, and this state-dependent complementary constant. But what especially by Deutsch in the 60s and other people, what they criticize is that these variances are maybe not the best measures for complementarity. The fact is that they depend on the unit, that they depend on the spectrum of the observables, and this kind of, this kind of gives some problem. It doesn't only depend on the POBM measure and how they're actually complementary. This complementarity. So this has been improved by Marcel Nuffink in the 88, and there is a 2 missing.
Minus 2. And there's an A.
Ah.
Okay.
Okay, sorry. Yeah, thanks for pointing out. Yeah, sorry, there's maybe sometimes there's something missing, like some squares. But I mean, his improvement was actually that he uses uncertain entropies to measure the uncertainty. These entropies only depend on the probability distributions, so they're not depending on the eigenvalue of observable. That's the invariant on the permutation, and that's this kind of nice property. And they have this kind of this state-independent bound. So this was a big achievement that we actually use entropy measures to quantify these uncertainties for this preparation of uncertainty relation. And this has been improved by using quantum memories, and finally it actually led to direct applications in quantum information. And this was also the point why I got interested in these relations, because we have these really fundamental principles, and from this principle we can actually say something about concrete applications in quantum information theory. We can show security of quantum cryptography. We can say something about entanglement and this. So it's this connection about fundamental physical properties and applications. Good. Let me now come to, my talk will be about measurement uncertainty. And the way I presented this preparation is because what I want to say is like that this measurement uncertainty up to kind of recently has been much less understood and much less be a topic in the quantum information science community. So most people only thought about preparation uncertainty relation, but not a lot has been done kind of from an information theoretic approach to measurement uncertainty. And that's why we got interested in it. Some people have worked on it kind of like, a positive formulation of actually finding operators or measurements which do approximate the position momentum measurements. So they're designing these measurements and see how good they perform. And another kind of really famous approach is by, started with Arthur and Kelly and then Appleby and also Ms. Osawa, who is here in the audience today. They had a kind of a noise operator approach to determine this inaccuracy or this error of these measurements. So, and this is kind of like, if I want to do kind of a measure, actually this is my C, is my actual observable, but I use the approximation A, then this has kind of a form like this. So I take this, the difference of them and square them. And there's some problem with that they're not always operational, because, if I take a square of the difference, this doesn't mean that this is actually observable of my experiment. So,
you compare with A before measurement and Z after. Your price will be that A and Z before measurement compared to after.
in this, yeah, but I cannot measure them jointly. I cannot measure this operator here. That's what I want to say.
The definition is
Are these definitions?
comparing the A before measurement, if you want to measure A.
Yes.
And you compare A before measurement and Z after the measurement.
Exactly.
That means that Z is replaced by U dollar ZU and minus A, EX squared. But you don't need U before the step.
Okay.
So you should write down the Heisenberg.
Okay. Thanks for pointing this out. Good. And then as we started with this project, our goal was actually to get information theoretic approach to this. So we wanted to have a clear operational motivated setup. We wanted to have operational error measures, which are always accessible in the experiment. And we also wanted to have our goal was entropic measures, formulating our errors with entropic measures. And this is especially interesting if one thinks about application in quantum computation. So in my talk I will first give a quick overview about some aspects of measurement uncertainty, go a little more into detail. Then I will show our new measurement disturbance relation, how we extended it to quantum memories, then applications. So measurement uncertainty, as I said, there are two concepts one can consider. One is joint measurability. It's the question of, I have two observables, X and C. The question, do I have a joint observable with outcomes X prime and C prime, such that actually, if I trace out C prime, if this X prime is equal to this observable here, and if I trace out X prime, this is equal to the observable here. And then we want to ask, we want to compare these kind of two devices here. Another question is measurement disturbance. In measurement disturbance, I have more like a dynamic setting, so we have an incoming state here. Then we have a channel or an instrument, which does has a classical output here, X prime, and then outputs like the same or like the same Hilbert space or system in the same Hilbert space, which then can be measured by a C observable. And the question here is how this kind of this extracting information about the X observable kind of disturbs the C observable. And what our relation will be about is about this measurement disturbance setting. And our relation will not have any kind of application to this joint. So, but I mean, that doesn't mean that we can now forget about joint measurability kind of uncertainty relations, because of course we can think about this sequential, this measurement disturbance setting as a sequential measurement, and in that sense, this joint measurement relation for here also applies to sequential measurement setting, and in that sense, we have that this also says something about the measurement disturbance, but it only says something if we are actually interested in quantifying the aspects how this setting acts or performs as a joint observable. And as we will see, this will not be the point we address in our relation. So, but because there was recently a lot going on about this uncertainty relation, and then one can divide into state-dependent uncertainty relations and state-independent joint measurement relations. And then there was by Bush, Lottie, and Werner, there was a lot of work about it, where they're using kind of like a worst-case calibration, so they're testing the state in certain calibration states, and then they compare it with the actual measurement. There has been a really nice result here by Buscemi, Haltesau, and Wilde, where they also use entropic measures, but this is also a state-independent relation, and they also have a really nice connection to an informational probability test. And there's recently one by Joe Rennes and Volker Scholz, where they use actually kind of CP norms to kind of compare these two kind of channels, these measurements as channels. And especially in 1 and 2, what this relation implies in the measurement disturbance setting is that if I actually have a channel that extracts information about X eigenbases, then they will necessarily disturb the C eigenbases. That's why they usually test their devices on X eigenstates and C eigenstates. There's also state-independent error disturbance measurement or joint measurement relations. This is, the relation, famous relation to Osawa. And there, these error methods, as I said before, they're based on kind of this noise operator approach. And the very nice insight here is that if we have a state-dependent relation, so this has to hold for any state here, it's like here psi, then we know that this actually has to be, this has to depend on the initial uncertainties. So there's actually some states in which this is, these errors are not sufficient. So we have to actually account for initial uncertainties. So, this was actually basically the situation up to 1 year ago. And then what we started to think about is that as I said, that we want to have some operational measure. And what we wanted to have is like that we have our error disturbance. So if we have this state here, so we have a C measurement we can apply X measurement, and we can apply this joint measurement in joint measurements. And then what we want is that having this scenario, we want to be able to test if there is a disturbance. If I have these devices, and I cannot see any disturbance by doing measurements, then we say there is no disturbance, because the things we are interested in is only the X measurement, the C measurement. No matter what happens if the outcome are not exactly the same, then I call them that there's no disturbance. And this was our operational approach here. And then also what we want to have, that we have faithful errors in the sense that we only, that the error is only zero if there actually is a difference. So if there's no difference between this random variable X and this random variable X prime, then we say there's no error. And the same for the disturbance. And what has been shown then recently is that in that case there cannot be any trade-off relation. So if you have this kind of, I mean, they're really strong assumption on our measures, but under this assumption there is no kind of like joint measurable certainty relation. Quantify this element. I mean, giving a trade-off. I mean, and this was the problem because some of them, they're not faithful in that sense, in these definitions. Yes, we have a system. Okay, I mean, but then, I mean, what was pointed out by Appleby already, that there is actually other different kind of like measurement error one can consider. So let's assume that we stick to our operational disturbance. Then we can either have this like, he calls it predictive error, so this is actually the measurement accuracy. So I'm asking, having this channel here, which extracts information M, and M now just be classical random variable, then how much M says about if I would just have done this experiment. So this is retrograde. This corresponds to the kind of accuracy of this channel here to measure X. But what can I also do? Asking a different question here. And this is called what he calls a predictive error. So one can ask how much information this M has about the future X. In that sense, it says something, I mean, how good you can predict the future X. And he also derived a relation in terms of variances for this kind of, for this disturbance error and this predictive. So, and this was, I mean, as I said before, this cannot work in our scenario, but we can of course ask, is there a trade-off between predictive error and disturbance for faithful error methods? And this will be exactly what we have done in our measurement. I mean, in our new relation, we quantified the disturbance against predictive. So the scenario is the following, I mean, as usual, so we have state rho is our input state. Then we have the channel E here, which has two outputs, the output M, which is just the classical value for now. And here we have the output, which we can do C and X measurements. So here the space is the same of being outputs of the channel. And then we also can do just no channel and just measure the C. So the operational quantities are given by these probabilities. So the C probability here, the C probability here, the X probability here, and then the joint probability of M and X. This will be our quantities, what the relation depends on. So then we define our disturbance method. As we said before that we wanted to have entropic disturbance measures. We define it, I mean, it's kind of, if you stick to entropies, it's kind of, if you want to compare to kind of like probability distribution, the first that comes into mind are relative entropies, because they take kind of like, yeah, that's how kind of what you can statistically compare to probability distribution. So we use as our disturbance measure, we use the relative entropy, and this has also, I mean, it has the statistical meaning hypothesis testing, and it's in that state faithful that it's actually only zero if they are equal. A side remark here is that we actually derived our relation for arbitrary Renyi value. So actually, the ingredients we need to derive this relation are really just depend on nice properties on this point. Our predictive error is given by the entropy. So this should tell us something on how much information M carries about this variable X here. And we quantify this by the entropy of X given this time. And the entropic measure we're using here is the conditional max entropy. I mean, I don't know, most of you maybe not know this quantity. It's a quantity from one-shot quantum information theory, and it's related to the 1/2 Renyi entropy. And actually we were hoping that it's possible also to use here a von Neumann entropy. But what it turns out is that it's not possible. That's why we have to use maybe not so conventional entropy measure here. But it is also faithful and has operational interpretation in the what's usually called data compression inside information. So how much information you need in order I mean, given you have access to n, then you can reconstruct x. And then, I mean, our relation looks the following. So for any channel here, you have that, and for any input state rho, you have that the disturbance plus here this predictive error is bigger than complementarity constant, and the constant here is the right square, luckily. So it's a state-independent complementarity measure for the observables, the same as in the mass-Newton. And then what we have to do is we have to reduce this quantity here by the entropy of this C variable. So it also depends on the initial uncertainty in this C variable. And it's fairly obvious that this has to be true if one looks at the qubit system. So let's assume we have Pauli X and C observable, and then F, this E here is a perfect X instrument, so it measures X and outputs the eigenstate corresponding to it. And then we can have an initial state which is a C eigenstate. In that state, of course the disturbance is really high because I do X measurement, but I mean the predictive error is of course from 0. So we have here a large disturbance. And here is also the fact, I mean, that H of C, I mean, this von Neumann entropy of this C variable is equal to 0. That means we have a strong bound. But if we now put in a state which is diagonal in X, then it looks, of course, completely different. So this measurement here induces no disturbance. So we have no disturbance and no error to the error. Actually, there is no bound on this equation. In that sense, this is equal to 1 over C, and it's not fitting itself. So I guess due to time, I will just skip the proof here and come to kind of a nice extension of our relation, which comes for free, is that we also kind of can include a correlated system. So we have a system S and then some correlated system R, which we refer usually as quantum memory. It means like it is isolated here at the system. And now I'm also asking how much disturbance this channel here introduces to the correlation between C and R. So of course, if we have this interaction there, this will destroy correlation of this C and R. And in that sense, I mean, if we extend this disturbance measure to comparing actually the distribution of C and R, and now this is kind of a classical quantum state, but you can define this relative entropy straightforwardly. So if you look at the distance of this C and R state and the one after applying the channel, then we have a bound which is actually now not reduced by the entropy of C, it's reduced by the conditional entropy of C given the system R. So this is really crucial in certain situations, especially if you think about, for instance, cryptography and so on. And I mean, as an example, think just about having a maximally tangled state here, and then if you trace out the R system, then the S system is just in a maximum mixed state. What happens in if we ignore this R system, then of course our bound will be trivial, so there is no trade-off in that case. But if we include this R system, then we have a fairly good trade-off, because we know then we have maximal correlation between the C outcome, and if you do a C measurement here, then we have perfect correlation, so we can actually check what disturbance has been introduced on the way here to this measurement. This is what happens. I mean, you can then easily see that in that case that this conditional entropy here is equal to 0, and we get this relation, which is now very strong, even though that the incoming state is just a mixed state. Looks like a mixed state. Then we come to applications. The one application we looked at, I mean, of course, we had this uncertainty relation, and we wanted to test how good it performs if we look at certain measurements. And one, I guess, canonical measurements is just thinking about putting a state which is inside a C basis. I mean, we have here a state here for R equal to 1. This is a C eigenstate, and then I'm having this kind of circuit here, and what this circuit does is just does a weak X measurement. So the tuning comes from this state here, so from this theta. So if I have a theta equal to 0, then I have a perfect X measurement. For theta equal to pi over 2, I have the identity channel. So no information about X is extracted. And then we can plot and see how tidy our relation is, what's the left and the right hand side. And we see that if this is a pure state, so this R, I mean for R equal to 1, we have a pure state, then we actually tie for all measurement strengths. And then of course, once we get more mixed, our income state is more mixed, that is what you would naturally expect, that it cannot be tied anymore, because we have already some randomness. So, and it's hard to tell if the randomness you see here, or even to use here, I mean, let's say, if here already have a lot of randomness, and this channel, I mean, even though it does a measurement, it uses not much more. So it's hard. So in that case, it gets not, I mean, of course, not tight anymore. But we can make it tight by just using our extended version with this quantum memory. And then we can show, if we just take the purification of this state here, and then our extended version, that is perfectly tight for all equals, for all measurement strengths. So let me just quickly say that our relation also applies to position measurement. I mean, observable, so this is the continuous spectrum. In that case, you just use differential quantum conditional entropies, and then it holds directly in the same signal form. Here, this is the complementarity is given by log. And we have this. I mean, from this we can derive a really nice example. If you look at a coarse-grained position measurement, where we just do a position measurement, we ask if there is, with a certain binning, and this binning corresponds to the interval of our precision. So if you have a precision of this delta Q here, then we can derive the following this, uncertainty relation, which takes the Heisenberg uncertainty relation kind of form. I mean, this is of course tricky here, because this D here depends not only on the disturbance of the momentum, it also depends on the initial spread of the momentum. Meaning that if the initial momentum is highly, peak is really sharp, then of course the entropy will be small, and then the disturbance will be high. But if the initial momentum is really kind of like spread out, then also this doesn't have actually. Then most part of the entropy is from this initial entropy you already have. So this is kind of like interesting because it gives the interplay between measurement and preparation. Good. So then I'd like to conclude. So I presented you new measurement disturbance relation with the property that the measures are actually expressed in entropies. So they may lead to some applications. We also have a different kind of trade-off relation. We don't look at the usual accuracy of the measurement. We look more at the predictive error, so how we can predict the future outcome. This can have possible application to quantum cryptography. Actually, one reason I was interested is coming from, in continuous variable, important is to use a reverse reconciliation system, and actually this corresponds exactly to this question. So can Eve actually predict this outcome of L4? So then, well, we also, then one can think, yeah, that's this point. So maybe it's also interesting to look at state-independent behavior. So this would maybe some future work. Good, so thank you for that attention.
Thanks, Fabian. Any questions? Can you show previous slides you explicitly mentioned in my one was wrong?
I didn't explain, I didn't say your work is wrong or something.
You mentioned that the problem was you said that the faithful error and disturbance should satisfy this relation. But your paper does not discuss any of this relation. And our error and disturbance satisfies this relation.
But not in all situations. So as far as I know, they have a explicit counterexample. But it's not satisfied.
I published the data on the types of origin in 2007, and
this means that if the random variable is equal, their condition is that they introduce the probability.
Yes,
This is not the condition for the equality of this random variable. If the random variable x and x prime is equal, it's not implies that the probability is not nothing. It should be the joint probability should be the direct. It's different. For example, you consider the iron. They have the same probability distribution, but they don't have the same value. So their criteria is not correct.
Okay, so I'm really happy to hear. I mean, maybe we can discuss this offline in more detail.
No? Okay.
That would be nice.
Okay.
Yeah? No? Thanks a lot for pointing it out.
Any questions?
Can you be more specific? Which one? Which paper? It's like
Okay, I think a quick question maybe.
Well, it's one thing slightly hard. So when we say the operation and the trade-off, so I understand that the quantities that appear in the trade-off are operations of time. But how does it mean that the one quantity is the other one shot? This is a trade-off.
sure. I mean, I completely agree, and this is actually, I would say, one of the points we were a little bit disappointed. I mean, because we want to have this phenomenon. But I mean, you can actually derive such a version. You could, but then you would have to switch the arguments in the relative entropy. And we thought like this is not so convenient because usually the measurement you do would introduce more disturbance. So it makes your distribution broader. But this, if you switch actually the arguments of the relative entropy, this would happen. I mean, it would often happen that it gets infinity. So that's actually a good problem, and we're still thinking about it. Yes, of course.
But we also have a relation that's valid
For one shot, yeah.
Or all meant for one shot.
Exactly, yeah. We have it for the Renyi entities, but the trade-off, I mean, then the lower bound, I mean, the entropy of the lower bound is also changed to the conversion. So this is how the trade-off is. Oh, that's a good point.